So square root decomposition happens when you want range queries to be answered efficiently. Okay, so if I give you an example, let's say you have an array, and in this array of size n, and the terrible drawing, I'm very sorry for that, but my board isn't working, so there's really no choice that I have except drawing terribly. In this array of size n, I'm going to get two types of queries. The first query is that increase, or rather change element at position x to p. So this is query number one. And the second type of query is to tell me all the elements from range x to y. I mean the sum of all the elements from range x to y. So this is basically a sum query. Okay. Does this make sense? Is everyone clear about this? I guess that people don't really care about this, but okay, I'll keep plowing on. So these are the type of queries we have. One of them is an update query. So update the element at x, a of x, to y. And the second query is sum all the elements between x and y and return us the result. So these are two types of queries. The brute force way to do this is to, every time you get an update, you just go to that position and you update the element at position x to y. So this is an order one operation. This is O1. Yeah, I should probably use a different color for complexity analysis. So this is going to be O1. And the sum query in the naive approach is going to be running through all elements between the positions x and y. So that's going to be a for loop between x and y. At most, this range can be of the size n because you run through the entire element. I mean, through the entire array. So x is over here, y is over here. You basically ran through the entire array, and that comes out to be order n. Now, as a question setter, what I can do if I want to be nice is to set all queries to update. But I'm a bad question setter, just like a normal computer programming question setter. So I set in the more difficult queries this way, order n. If you have q queries, then each query is taking time n. So you have total complexity of q into n. Now, how do we improve on this? One of the ways to improve our, the biggest problem here is not the update. The problem is the summing. Summing is taking too much time. So what we want to do is we want to sum queries fast. Up to this point, is everything clear? Let me, again, like a teacher, head back to the classroom and ask students, is everything clear till now? Okay, wow, from 200 people, it became 137 people. That means people are not interested in square root decomposition. But what had I promised? Yeah, do I really care about subscribers and views and everything, or do I care about sharing knowledge? Now, should I be naive? No, let me be noble online at least and say that I don't really care about subscribers. I'm going to go to the study material. And so what we're going to do is we are going to actually try to optimize this bit. Right? There's two things we can optimize. This is impossible to optimize. This is constant time already. And the query time for the sum query is too expensive. So I'm going to try to bring down this order n. Now, if you have done a little bit of computer programming especially, then you'll know that when you need a lot of sum queries to be answered, different ranges x to y and multiple sum queries coming in, if the array is not being updated, this is a straightforward thing. If the array is not being updated, what you can do is pre-calculate sums. What do I mean by that? Well, let me just draw it again. Yeah. So you have the array up till this point. And let's say you have these boxes with the elements -1, 2, 8, -3, 5, and 7. Okay, now if I give you a sum query between these indices, what's going to happen is you'll need to run through all of them. But I don't want to do that. So instead, I'm going to use a smart calculation. I'm going to say, what's the sum between elements 0, 1, 2, 3, 4, and 5? So what's the sum of all elements between indices 3 to 5 is the query. And the answer to this is the sum of all elements from 0 to 5 minus the sum of all elements between 0 to 2. And we can make this calculation because effectively this range is equal to this entire range minus this range over here, 0 to 2. And so if we can subtract from the upper range the lower one, then we'll be getting the target range. Yeah, and because it's a contiguous block of elements, this makes sense. Sum of all elements between 3 to 5 can be gotten by getting the sum of all elements between 0 to 5, subtracting from that all elements between 0 to 2. Okay, now that we have that, we have this, this understanding, what can we do to speed up our queries which are taking order n time? Well, we can pre-compute all the sums from 0 to an index position I for all I. You see here that whenever I give you an, this is not x, this is y, and this is x minus 1 basically. Whenever I give you an x and y, that time what you need to do is find the sum from 0 to position y and from the sum of all elements from 0 to position x minus 1. So if I am able to find the sum of all elements between 0 to I, where I ranges from 0 to n minus 1, then I can answer this query in order 1 time, and this query also in order 1 time. Subtracting them is an order 1 operation, and therefore the query time will reduce to order 1. Okay, does this make sense to people? Yeah, this is a common technique called, yeah, called drawing, no, called prefix sums. I'll be sharing some relevant links in the description after this video is done. So prefix sums it is. Does this make sense, guys? Clear? Oh wow, yay! Make sure you explain what happens if this. Okay, I'll read that later, please. Thank you. Perfect. So what I've done now is reduce the query time to order 1, and the update time was order 1 already. So if we have q queries, now the order complexity comes down to order q. And this is great because q is of the, let's say, size 10 raised to the power 6 or 10 raised to the power 6, yeah. If this is the case, order q is enough to pass in 1 second. And so this problem is solved. We don't even need square root decomposition. But not really. The problem here is that this is wrong. Our assumption for updates being in order 1 no longer holds. Let's see why. Let's say that there's an update at this position, position 2. 8 becomes 7. Yeah. Now, I haven't actually calculated the prefix sum, so I'll do that over here in this separate array. We'll need that for getting the prefix sums, right? We were pre-computing this. Rather this sum of all elements between 0 to 1. The sum of all elements between 0 to 0 is minus 1. Yeah, just have a look at this guy. Then you have the sum of all elements between 0 to 1. How do we calculate that? We have a look at this element and add this, the element in position I to that. Okay, so we get here 2 minus 1, which is 1. Similarly, we take this element 7 and then find out the addition of these two elements, which becomes 8. With this, it comes out to be 5. 5 plus 5 is 10. And finally, we have 10 plus 7, which is 17. Okay, so that is the prefix sum calculation. But whenever there's an update, so I'm going to redo this. So 7 is now made 4. what I need to do is I need to update all of the prefix sums at and beyond it. The reason for this is all elements before it from 0 to if the index was x, from 0 to x minus 1, nothing is changed because their sums are still the same from 0 to x minus 1. However, when you go ahead, you'll need to include this element from 0 to that element, right? So the problem is the prefix sum array has to change. So instead of 8, I now need to recompute this. So 4 plus 1 becomes 5, minus 3 plus 5 becomes 2, 5 plus 2 becomes 7, and I get rid of 10, which is over here. 7 plus 7 becomes 14. Let me just scratch that out and write 14 neatly. This is the worst handwriting I've had since 3rd grade, and that time I used to get rapped on my knuckles by teachers. It was a pretty violent time, but I think now looking at my handwriting, I really deserved a little more than what I got. But anyway, you get the gist. What happened over here is that because of this element changing 7 changing to 4, or rather 8 changing to 4, all elements beyond this point were changed. And I can pick up any index x to update, to any given value y. And the total time required to update all elements beyond x can be, in the worst case scenario, index 0, all elements beyond it are the whole array. So the update time is not order 1, but it is order n. So we are at some sort of a mirror image. Earlier we had order 1 update time and order n query time. Now we have order n update time and order 1 query time. Yeah. So with this mirror image, we really haven't made too much progress, because what can still happen is that because question setters are such bad people, they can put in half of the queries being updates, which is order n, and half of the queries being sums, which is order 1. So it's still, in the worst case, order n into q. Right? Up to this point, is everything clear? Okay. I don't really know about this, so I'll just hide it. Question lead code, I'm not able to optimize it. Okay, this was not the right place to ask this question, so you're out. Anyone else with a sensible question, please? Make sure you explain what happens. Okay, guys, perfect. So the coding guy is finding it a little bit slow. The thing is, if it's the first time in your life you're going through range queries, I have to take everybody's learning speed in consideration. So I think this speed is fine. Yeah, guys, great. I just talked to myself. Okay, but I'll just have a, yes, it's clear. Perfect. So now let's get to the hard bit, which is square root decomposition. So there's two things that we can do. One is range queries using segment trees here, but I'll tell you what, Rachit Jain is actually having a one of his videos coming out on segment trees soon. So initially, I don't know how many of you guys saw it, that this was designed to be a segment trees question video, but I had to switch it to square root decomposition very soon, because Rachit just informed me that, hey, this is a segment tree question I'm coming out right now. Coming out with right now in a few days. So that's the reason why we have changed it to this. Square root decomposition is more complicated than segment trees in a way, because it's maybe not as, let's say, intuitive. Yeah, thinking about why square root decomposition should be used. So, okay, Ajay has a doubt. Okay, Ajay, please ask me the doubt. You'll need 60 seconds to actually ask me the doubt, because I have kept it at slow mode. But yeah, as I was saying, square root decomposition is something which is used for advanced questions. Usually, maybe maybe questions which can't be solved using segment trees, you can go for square root decomposition. One of the good things about this is it has a really low constant factor. So if you know about segment trees, but if you want to get a question solved quickly, not just through coding, but also through, the effort that you'll involve into getting the correctness proven, then just go for square root decomposition. Yeah. Okay, okay. I'm sorry, Gaurav. I'm not so great at Hindi, and I don't think I can explain using Hindi. Okay, guys, just absorb the previous attempt, and now let's go for square root decomposition. Ah, perfect. Ajay has asked this doubt. If range xy for Q2 is entire array, then order n only. Now, how order one? Uh, well, if the second query you mean the sum query is x to y, which is the entire array, it is still it's still order one because you have the prefix sum. So I mean the entire array, but the prefix sum is giving you the answer in order one because the last element is what you're looking at, right? And you want to subtract from it this the remaining range. The remaining range is null because the entire array is in. So you don't need to subtract anything from it. You can subtract zero from it. So this is what comes out, right? You can work it out. It's going to be order one. Prefix sums are order one for some queries. By some I mean SUM. Okay, enough pondering. Let's head to square root decomposition. We take this original array, and can I get a rectangle here? Ah, okay. So I'm going to draw as straight a line as I possibly can, and break this array into its elements. Okay. Now let's give numbers to this: -1, 3, 8, 2, 7, -3, 4, 2, 9. And the indices are set to 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so this array, as you can obviously see, is of size 9. Now, square root decomposition says that we are going to break this array into pieces, and with each of those pieces, depending on the query that we are getting, whether it's an update query or a range query, we can then perform some operations on the pieces of the array. So as you can expect, square root decomposition, like the name suggests, square root, that means we are going to break this array into square root blocks. The size is 9, so we are going to take the square root of 9, which is equal to 3, and break the array into blocks of size 3. So length of a block, or rather size of a block, which is equal to b, is equal to 3 in our case. Yeah, square root of size of array. So I just broke it into blocks of size 3. Now I'm going to be storing some value which can answer the query for this entire block. And because we have some queries, sum from x to y, I'm going to be storing the sum of all elements in this block. Yeah, that's one obvious value to store here. So that's going to be -1 plus 3, which is 2, plus 8, which is 10. So that is the value here. Over here we have 6, and over here we have 15. Yeah, we are storing a representative value for the entire block. Now, whenever there's an update query, let's say this element is being updated to 8. All I need to do is look at this value, 6, and just add 8 to it, 6 plus 8, and subtract the old value from it, which was 7. And I have my new sum now, which is going to be, okay, I kind of, I'll use a different color. So this is going to be 7 in total. All right. once I made this thing 8. So updates are really fast. Updates are order 1. Yes, this part is clear because I made 7, 8, and all I did was just add the newer value and subtract the older value. Also, queries are going to be fast. That's the interesting thing. How a query is going to be fast? If I give you a range like this, yeah, from 3 to this element 4, from index 1 to index 6, give me the sum of all elements. What am I going to do? I'm going to come to the block where 1 exists, which is this block over here. I'm going to ask it, is my range from 1 to 6 completely covering your block? And this block is going to say, no, it doesn't. So run through all indices from 1 to the end of this block. That is 1 and 2. That gives me 3 plus 8. So I go to the sum 3 first. Plus 8 gives me 11. Now I go to the next block because the block has ended. So I come to this block and I say, is your range entirely encapsulated by my query range? And the answer to that is yes. So all I need to do is add this sum, because this sum is the sum of all elements in that block. I don't need to run through the entire block. I just do a plus 7. I make some savings, right? Instead of 3 elements to add to this sum, I just add 1 element, this one, the outer thing. And finally, I come to the last block and I say, is my range within, is my range entirely encapsulating your range? And the answer is no. So I go inside and I start running from 6 to the end of my range. Yeah. And so I have the element 4 plus 4. And effectively, I have 22 with me as the sum. And if you just run through this, you'll see 10 over here, 18 over here, 21, 25 minus 3, which is 22. So that's the correct answer. What are the benefits of doing it this way? Well, over here, instead of running through the entire block in our naive approach, if you remember the first approach we had, it was order n. Now, there is one block which will have the starting range, incomplete starting range, and one block which will have the incomplete ending range. Why is this? Because a range is contiguous. It has to either entirely encapsulate the block or partially be encapsulated by the block. If it is partially encapsulated by the block, there's just 2 blocks which are going to partially encapsulate it, the starting and the ending blocks, right? Is this point clear, guys? Okay, I'm just gonna, perfect. So, all right. In fact, Pedro Silva, there's an explanation. I'll give you the explanation why it is square root and not any other value. This is pretty interesting. And I think I don't think I had discovered it by myself, why it is done. Of course, I haven't discovered square root decomposition. The person who had made this was a genius. But I have independently found out why it is square root of n. And I'll tell you why. So this reduces the time complexity to the number of blocks you can have. Basically, a lot of the blocks will be falling in the range that you have, which is entirely encapsulating it. So order the number of blocks. How many blocks do you have? B is equal to square root of n, right? That is the size of each block. So the total number of blocks you can have at most is n by square root of n. So the total number of blocks you will have is of the order square root of n. Okay, plus the 2 blocks which are on the edge, this one and this one. Now, how many elements will you actually run through on these blocks? Each block is of size square root n. So the maximum number of elements you'll run through in any of these given blocks, 2 of them at most, is square root of n. So 2 square root n. You see that this is coming out to be 3 square root n in total. And basically, the constant factor can be ignored. So it is order square root n. Yeah, so your query times have reduced to order square root n, and this is extremely fast. So what you can do now is answer the range queries very efficiently. Updates in order 1 time, queries in square root n time. So the total complexity, time complexity, is going to be order q into each query at most is going to take root n time. So order q root n. And this is very fast. If n is of the order 10 raised to power 5, and q is again, let's say 10 raised to the power 5, then q root n will take you approximately 1 second on the modern processors that we have. Does this make sense, guys? Or do you have any doubts? Yes, we have to look for the incomplete block, Anthony. The reason for that is because there's going to be, usually there are two blocks which are incomplete, the starting and the ending ones. And the reason for that is it's a contiguous sequence, but we can't predetermine where the ranges will be. So we have broken into sizes of square root arbitrarily, and the range can start from here also and end here. So this will be the ending point and this will be the starting point. The good news always is whenever we have a block which is entirely encapsulated by our range, we can answer that in order 1 time. And so at most we'll be hitting the total number of blocks, which is n by root n, which happens to be root n. And for all those blocks where we have to traverse the incomplete blocks, they are of size root n. So we have this as our time complexity. And that comes out to be order root n. All right, and the updates, as we discussed, is just updating this value. Perfect. I think most of you have gotten the idea. Mayank, you can have a look at the square root decomposition. I think I've already, I'll share a link with you guys for the implementation of this. This is actually quite easy. So I'll just share that with you. Do we have to loop for, okay. Edge blocks, yes, that is true. What kind of problems can we solve? Lots of range query problems can be solved using square root decomposition. Every problem which can be solved using segment trees can be solved using square root decomposition. Every problem which can be solved using square root decomposition may not be solvable using segment trees. So it's a more powerful technique than segment trees. However, the obvious drawback is that it has a q into root n time complexity requirement, and segment trees, as you know, requires just q into log n as the worst case time complexity. So there is an additional complexity charge that you have, but it's a more general algorithm and can solve more problems. I think if you find it in between coding guy, you just run through all elements in that block. So if this is the range, this is the range which is incomplete, then you just go through 6 and 7. You find the sums and then you just answer. Okay, that comes out to be 4, right? Or was it something else? Well, yeah, basically you just run through these 2 elements. Okay. Now let's see why square root is the answer. Yeah, if you guys are sure. There's segment tree questions which you can't solve with square root decomposition. I don't think so. 4y there. But if you can give us an example, that would be great. I would like to have changed my mind like Steven Crowder. Okay, perfect. So let's figure out why square root decomposition. So if someone asks you that, hey, why square root decomposition? Why not cube root decomposition? And this question is useful to answer if you are doing some really advanced comparative programming. It actually helped me understand Moore's algorithm, and also why Moore's algorithm with updates requires n raised to power 5 by 3 as the time complexity. Yeah, it's no longer square root, it's this weird number. And you can check out my algorithm, video with Moore's algorithm with updates for the understanding of why that is the case. But now let me come to you and say, why choose square root? So why choose a block size of any value? So this b is going to be the size of a block. Okay. And what we are going to do is we are going to choose an optimal size of B. Let's assume that someone comes to you, gives you an array, and says that I need you to break it into blocks, but find me the most optimal block size where you're going to run your original algorithm of square root decomposition. So an optimal block size is what we need. B is that size. We don't know what B is, but we do know that if we choose a block size B, then the array is broken into n by B blocks. So this is the number of blocks. Now, we have these two numbers, and we do know that the question setter is going to give us a query of type update. Yeah, whenever there's an update, or yeah, I mean, when things get a little complicated, what happens is update is going to be more than order n, but let's assume that it is q into 1. And on the other hand, we have queries. So queries is q into the number of blocks that we'll need to touch, yeah, n by b. These are all the blocks which completely encapsulate, I mean, are encapsulated by our query. We don't need to go into them. We can just look at their outer value and answer, return an answer which will be adding to our original answer. So if these are the representative values for 3 blocks, we just go through them. So the total number of blocks is going to be n by b, and all the intermediate blocks are going to add at most n by b computations. On the other hand, the edge blocks, so to speak, the incomplete ones, are 2 in number, yeah, starting and ending. And so we have 2 into size of those blocks, which is 2 into b. This is the maximum we can have. So now q into 1 is obviously smaller than this number, so we are just going to ignore this number. And we're going to focus on this number, right? Where we want to optimize the value of b. We want to reduce this value to as little as possible. Because q is a constant and we can't change it, what we are really interested in is just changing this value. So we have with us n in by b plus 2b. Now we want to find a value for b. So I'm going to do something. I'm going to do a neat trick. N by b plus 2b. And to minimize this value, I'm going to differentiate the value with respect to b. At a maximum or minimum point, this will be equal to 0. So let's differentiate this and equate it to 0. We get n by b square with a minus sign over here plus 2 is equal to 0. This gives us that 2b square is equal to n, which means b is equal to root of n by 2. Okay. Now give and take a little bit, and I'll tell you that b is equal to root n works perfectly fine. This is not exactly optimal, but there's a lot of constant factors that we haven't taken into consideration when doing an n by b. What about going to a different value and so on and so forth? What about figuring out whether the range is entirely in or not? So those things, constants, if we ignore that, if we ignore this 2 and come to this value, b, we get this to be 1. And I'm just showing you why it is square root now. So the 2 vanishes over here, and over here we have b square equal to n, and that turns out to be b equal to root n. This is an approximation. The optimal was coming out to be root of n by 2, but we have taken an approximate best value, and that's why we do a square root decomposition. Okay, is this point clear? Perfect. So that's it. That's the reason why we have square root decomposition instead of cube root decomposition. And how do you like the entire like explanation? If you guys have any doubts, then just tell me. I'll just clear it on the spot. Hmm. There's some video link over here. Ah, no. Karthik Nayak. Well, you might have had a good link. I'm not entirely sure, but let's see. Okay. Okay. I can't really see. Can I solve a question not solved by secretary? Well, have a look at this. Archit and small some some hacker earth question. Actually, hacker earth had contacted me asking me to make a tutorial on this question. So hacker earth, little Archit and magic arrays, I think this is the question. And it can't be solved using segment trees. It can be only solved using square root decomposition. So you can have a look at that. Oh, why you had to differentiate, Anthony? Because when you differentiate, you get a maxima or a minima. So that's a good question. D of some value, let's say A, when differentiated based on X, is going to give you 0 only when your graph has a maxima or a minima. The reason for this is because when it goes to an extreme, it starts falling. And again, if it goes to an extreme, it starts climbing. So whenever it starts falling or climbing, there's a point when there's a transition. Yeah, and when you differentiate, you're basically taking the tangent of this. So this line is going to be, with respect to the function, it's going to be 0. Yeah, that's the best I can tell you. The tangent is sloped at 0. It's going to be parallel to the x-axis, and that's why it's either a maxima or a minima. Now, how do I prove that this value that I just got is a minima? The reason is because if you differentiate it again, so d of d square a, then you get of x square. So like, yeah, you differentiate it again. Then what you will get is, as you can see over here, it's increasing. So the slope, the change in slope is increasing. So this is greater than 0. And that's what happens. The example we had was minus n by b square plus 1. If I differentiate this with respect to b, I get minus becomes plus 2n by b cube. Yeah, and this is a positive quantity. As you see, I've differentiated again and gotten the positive. So that means that this is a maxima. I mean, rather, this is a minima. So I have minimized the cost of the computations I have.